Alright, so today we're going to be taking a look at the popular Leetcode problem, word search. And so what this problem is asking us to do is we're given an n by n grid of characters called board and a string word. And so our goal is to return either true or false if word exists in the grid. So as the name suggests, we are searching for a word search. Now the constraints that we're given for this problem is the word has to be constructed from letters of sequentially adjacent cells. So the adjacent cells are either horizontally or vertically neighboring, and the same letter cell may not be used more than once. So in the context of this problem, how does this all play out? Well, let's take a look down here at our example. As you can see, this is our board, and we're given a string word, ABC, CED right here, and the board is constructed like so. It is a 2D array, or a matrix. And so we're essentially searching for this word in this board. But exactly how does this work? Now, I'm going to be upfront with you, there isn't really an efficient way to solve this problem. In fact, the only way to really solve a problem like this is to explore every single possibility in our board to see if we can actually find the word that we're looking for. And so when you're dealing with a problem that has exhaustive search, that's known as a backtracking problem. We're essentially checking all possibilities within our board. Alright, so let's take a look at how something like this would work. So with backtracking problems, we start from the ground up. So in this case, we're going to start with the first letter. We're going to look for A. So let's just say, for example, that we start at E. So we start at E, that's not A, so then we look at an adjacent cell. So let's say we look at C, that's not an A, move over, look at B, that's not A, and then finally we find an A. So now that we found the first letter of the word that we're looking for, we need to start exploring neighboring cells so we can find the next letter, in this case B. So remember, when we explore neighboring cells, we look horizontally or vertically. So in this case, we would look up, left, down, and then finally right, which is B, which is the next character that we're looking for. And then the backtracking process continues. So we look up, nothing there. We can't look left because, remember, the same letter cell may not be used more than once. Also, there's really no point in looking at A because we know it's already in our word, we've already found it. So we can effectively just ignore this from our search. Then we can look down at F, which is not in our word, and then finally we will look at C right here, which is the next character we're looking for in our word. And that's pretty much how this process works, and we do that until we've essentially exhausted all neighboring cells, eventually finding each letter in our word, until we're finally able to construct the final word itself. And so that's an overview of how we're going to solve this problem. One last thing before we jump into the code. The way we're going to solve this problem is with backtracking, but more specifically, we're going to be leveraging depth first search, or DFS. Depth first search works perfectly with backtracking because we're still going to be looking at all adjacent cells. It just offers us a structured and systematic exploration of the matrix. DFS allows us to essentially prune redundant paths and terminate exploration when we don't find the next letter in our word. And generally speaking, in coding interviews, when you implement backtracking does make use of DFS. So we can kill two birds with one stone by learning about backtracking, but then also learning about the concept of depth first search and how it applies to matrices. So without further ado, let's jump in the code. Alright, so the first thing I like to do for these backtracking type problems is declare constants for the length and width. So in this case, we can just call it rows and calls, and this will just be the length of the board and length of board 0. And I'm putting it in line like this because this will map to rows and this will map to calls. This just makes it easier so when we reference rows and calls in our for loop, we don't have to actually write out length boards or length boards 0. Essentially, it just makes our life easier. And then remember, we can't be using the same letter twice, so we need a way to keep track of that. The easiest way is by implementing a set. Now, if you don't know what a set is kind of like a hash map, but it weeds out any duplicates. So with that out of the way, now we can write our DFS function, our depth first search. So another thing I like doing with these backtracking problems is writing a nested DFS helper function. So we can start out like this. We have our DFS function, which will take our index of I and j, and then we will include k, which is the current index of the letter that we're looking at, or the character that we're looking at. So the reason we pass these indexes in is because we want to be able to look at adjacent cells. And so the first thing we have to do in our DFS function is check if the indices that we're looking at are within bounds and the current cell matches the word character. And so we can start that off by saying if not 0 less than or equal to I less than rows, or not 0 less than or equal to j less than calls, or board I j does not equal word k or ij in visited. Now I know this may look confusing, but the first part of this checks to see if we are out of bounds or if the current character that we're looking at in the board is equal to the current character in our word that we're trying to match, or if we've already visited a particular character. If any of these are true, then we simply just return false. This helps us break out of a DFS search early if we end up going in a direction that we don't want to. In other words, if we are either exploring out of bounds, or if we're looking at a character that is not the one that we currently need, or if we're currently looking at a character that's not in our word string, or if we've already visited that character. So having an early check like this is important. Next thing we need to do is have a case in the event that the entire word is found. If this happens, then we can return true. Now the thing to note here is that K will always keep track of the current index of the character we're looking at in our word string. So if we reach the end of that string, so length word -1, because strings are zero index like an array, so once we reach the end of that word, if K is equal to that, and that means we've effectively explored all the paths in our board and have found the word that we're looking for. Now again, we put this at the top because we want it to be one of the early checks we make before we start actually traversing and doing a bunch of work. So this helps cut back on runtime. So the next thing we want to do is add the current position to our visited set. So that'll look like this: visited.add, and then we will add the coordinates in our matrix of I and j as a tuple to our visited set. So this just helps us keep track of the current coordinate or position that we're visiting. So when it comes to DFS functions, these are all pretty standard checks. You always want to make sure that you're not going out of bounds or that something isn't wrong. We also want to have a positive exit condition in the event that we meet all of our criteria. And then we also want to start by adding whatever it is, in this case, our position, to our visited set to make sure that we aren't checking characters we've already looked at. So once all this is out of the way is when we can actually start doing the exploring. And so this is where we'll be recursing with our DFS. So first we'll declare a variable results, and then we will start declaring multiple instances of our DFS function, but with different inputs. This will help us traverse in the different adjacent directions. So that'll look like this. We'll start with our DFS, and then we can say for this one, I plus 1, j, k plus 1. Now we have to increment k because every time we search, we're potentially looking at another letter, so we have to make sure that k is being tracked properly for our word. But in this variation, we're just advancing the I index plus 1, leaving the j alone, and then performing our check, which will then run all this code again, and then check all adjacent cells. Now, this isn't the only check we make. We actually have to do 3 more, because remember, we have to check in all 4 directions, horizontally and vertically. And so these will all look very similar to each other, so let me just copy and paste them. All right, so this is the end result of our exploration. As you can see, we have the DFS function declared 4 times here, and it checks in each cardinal direction. Seems really repetitive, but this is how we do it. But it's not over just yet. We also need to make sure we remove the current position from our visited set when we backtrack. The general rule is whenever you add something to the visited set, you also want to remove it after doing your exploration. This is just considered general cleanup. So that'll just look like visited.remove, and then we'll just remove the tuple I, j, or the coordinate I and j. After everything is said and done, we will finally return our results. So this is pretty much the DFS function for this problem. So now the next order of business is to iterate through each cell to start the DFS exploration. So we can simply do that with a nested loop, which will look like this. We can say for I in range of rows, and then for j in range calls, if DFS I, j, 0, return true. Essentially, this nested for loop allows us to look at every single coordinate within our board and then run the DFS on it. And so by doing this, we're exhausting every possible direction and every possible combination of letters to eventually find our final word. Like I said, this problem isn't very efficient because we're going to be exploring every single possible combination of words within our board. And then if the DFS returns true, then we of course return true here, which means that our word was found within our board. And then finally, we have to have the case in which we don't find anything, or we don't find the word that we're looking for, which in that case, we just return false. And so that is the code solution for the word search problem. Now, before I end this video, I of course want to talk about the runtime of this problem. So as I've mentioned before, the runtime for this solution isn't going to be very efficient. But in either case, let's take a look. We know that we're going to be dealing with a board the size of m times n, which is the length and width of our board. Then we also have another consideration to make. As you can see, we have DFS running in the 4 directions to look at the adjacent cells of every coordinate that we take a look at in our board. So since we're going to be looking in 4 directions, we can start with 4, and that will be to the power of the length of our word. Now, why is this? Because in the worst case, the length of the call stack for our DFS recursion is going to be the length of the word. And we can shorten this by saying instead of length word, we can just say n. So the overall runtime is O of n times 4 to the n, which covers the size of our board that we're going to be traversing through, times 4, because this is the 4 directions we're going to be exploring, to the nth, which n in this case is just the length of our word. So adding this all together, this is what we get. Again, like I said, not a very efficient runtime, but it is what it is. In any case, I hope you guys learned a lot. Hope you learned a lot about backtracking and DFS, and I really hope you can internalize this sort of template that I use for solving backtracking problems. Because once you identify that you're working with a backtracking problem, you can pretty much just plug and play this template that I have. Remember, starting with defining the length and width of the search space that you're working with, and then declaring some sort of visited set, and then having an internal DFS helper function, which follows this criteria of checking for out of bounds, declaring an exit condition, adding to visited, in our case, checking in the 4 different directions, removing from visited, and then finally returning the result. And then after which you will apply that DFS to every coordinate in the search space that you're working with in your matrix. So you have to have a nested loop, and then if DFS with just default inputs, and then either return true or false. So again, hopefully this all made sense, and I hope you guys learned a lot, and I'll see you in the next one.